Okay, have you ever really stopped to think about how your computer actually understands code? I mean, we humans just make up these languages, type them in, and somehow this machine, this collection of silicon and metal, just gets it. It feels like magic, right? Well, today, we're going to pull back the curtain and show you the trick.
So let's imagine for a second we invent our own programming language. We'll call it, I don't know, ShadowScript. And in ShadowScript, we write a simple command, something totally readable to us. Make variable c equal to a plus b.
And just like that, the computer understands. If A was 10 and B was 15, boom, it knows C is 25. It doesn't ask any questions. It just does it.
So how? How is that even possible? We wrote something in a language that didn't exist 5 minutes ago, and the machine just gets it. Well, I promise you, it's not sorcery. It's actually a really brilliant, logical process of translation.
Okay, so to really get the solution, we first have to appreciate the problem. And the problem is huge. You see, humans and computers speak fundamentally different languages. Our world is full of concepts, grammar, and ideas. Theirs, it's just raw electricity. It's wild to think about, but if you could shrink down and look inside your computer's processor, you'd just see billions, literally billions, of these things called transistors. And all they are, really, are microscopic little switches. Super fast light switches, basically. They can either be on or they can be off. That's it.
And we as humans represent those two states, on and off, with a 1 and a 0. This is it. This is the computer's native tongue. It's called binary. Every single thing your computer does, from loading a web page to playing a game, it all boils down to an unbelievably long and complex pattern of just ones and zeros.
But here's where it gets really clever. We start combining these simple on-off switches into slightly more complex things called logic gates. Think of them as tiny little decision makers. Like an AND gate will only flip to on if both of its inputs are also on. And by combining these gates over and over, we can build circuits that do math and even store information. This is the machine's true language, built up from the simplest possible foundation. And that brings us right back to the Great Divide. How in the world do we bridge this enormous gap between our abstract idea of make a variable and the computer's simple world of ones and zeros?
Well, the short answer is we don't cross that chasm. We build a bridge, and that bridge is a special kind of program called an interpreter. Its whole job is to be a real-time translator between our language and the machines.
Now, this translation process isn't just one big messy step. Nope, it's a really elegant 3-part assembly line. Each stage has a very specific job to do, one after the other.
So step 1 is called lexical analysis. You can also call it tokenization. Think of the interpreter acting like a meticulous editor. It scans our raw code, which to the computer is just a meaningless jumble of characters, and it breaks it down into individual, meaningful units, or tokens.
So for example, a simple little expression like 5 plus 3 stops being just 3 characters. After this first step, it becomes a structured list. The computer now sees it as an integer with a value of 5, a plus sign operator, and another integer with a value of 3. You can see how it's already starting to make sense of our code, right?
All right, next up, parsing. Now that we have all our words, or tokens, the parsing stage is kind of like diagramming a sentence back in English class. It takes that flat list of tokens and figures out how they all relate to each other based on the language's grammar rules. It's all about building a structure.
And for anything even slightly more complex, this structure is absolutely crucial. I mean, think about this expression. If the computer just read it from left to right, it would get the wrong answer. It needs to understand the proper order of operations, just like we do. And this is the really clever part. The parser builds what's called a tree, and it builds this tree to respect the rules of math. So it knows multiplication has a higher precedence than addition, right? So it puts the 5 times 2 part on a lower branch of the tree. This is a visual instruction that tells the computer, hey, solve this part first before you move up and do the addition. So finally, with this beautiful, perfectly structured tree, the interpreter can get to its main job, actually running the code. It does this by walking through the tree and carrying out the instructions it finds. It walks this tree in a very specific order. It starts at the bottom and works its way up. So it'll look at that lower branch, solve 5 times 2, and get 10. Then it moves up the tree and solves 3 plus 10. And that is how it gets the correct answer, 13, every single time. That structure, that tree, is the absolute key.
So when you peel back all the layers, what have we really learned?
Well, the magic of a programming language, it's just a really well-designed system for translation. It's an illusion.
Now, our little shadow script language uses an interpreter, which is like having a live translator whispering in the computer's ear, line by line. But there's another way to do it, using something called a compiler. A compiler is more like a translator who takes your whole book, translates the entire thing into the other language at once, and then hands you back a finished copy. They both get the job done, just in different ways.
And really, that's the whole takeaway here. A programming language isn't some mystical spell that a computer just magically knows. It is a carefully constructed, logical, and frankly, beautiful bridge that we humans designed to communicate our complex thoughts to the incredibly simple, yet powerful logic of a machine.
This three-step dance of breaking down, structuring, and then executing, it's the secret behind almost every piece of software you've ever touched. And it kind of makes you wonder, doesn't it? What other magic in our world is really just a clever system hiding in plain sight?